by doing. We are headquartered in Seattle, Washington State, and we have an R&D office in Romania. That's where I'm from. How do we achieve our mission? We provide whole package with design and manufacture development kits that customers can use to learn new technologies. Apart from hardware, we provide software packages too, IPs, all open source, and technical support. Some of our products, we have FPGA and microcontroller-based development kits, also peripheral modules like sensors, image sensors, and instrumentation products like Analog Discovery 2, which is widely used in academia and industry. Some example of software and support that we provide for free. There is a set of workshops on digital-related subjects like embedded vision or analog and digital signal processing, textbooks for digital design learning, and online platform support for our customers with all information needed in the design and innovation processes. We have online store, but on non-US market, we work through distributors. You can find more details on our website at DigiLent.com. We began to grow a community around our products, so I invite you to visit our forum at forum.digilentinc.com. There you will find enthusiastic people involved in digital design and electronic related projects. Also, we have tight relationships with one of the most important players in embedded world industry. We work close with them to develop and innovate new products for engineers around the world. So, which was the idea behind this project? Well, we wanted to come up with a project that tests the suitability of our hardware platform for artificial intelligence-oriented applications. For this purpose, we chose a well-known and accessible neural network-based project, handwritten digit recognition. In this way, we want to offer a starting point for engineers and students from which they can develop new ideas in AI field. Our task was to design an embedded system that takes a picture of handwritten digit and provides a guess live. We started from a well-known hands-on textbook in neural network and deep learning area. We validated the results against NMIST database, and the implementation was feasible using readily available hardware from Digilent. So neural networks are one of the most beautiful programming paradigms ever invented. Using this approach, we design a system to learn from observational data how to solve our problem. This is quite different from the conventional approach to programming, in which we tell the computer what to do by splitting the whole problem in small independent tasks that the processor can perform easily. Between 1950 and 1960, the perceptron was widely used for binary classification. Using a single layer, the perceptron could not be trained to recognize many classes of patterns, causing a stage stagnation in this field. In 1969, it was shown that it's impossible for this kind of network to implement an XOR function, being limited to learn linearly separable patterns. But in 1975, the backpropagation algorithm renewed the interest in artificial neural networks because it effectively solved the XOR problem. This made the training of multi-layer networks feasible and efficient. In 1999, it was proved that multi-layer feed-forward network can implement any function, and the zip code recognition algorithm was developed. But in the mid-90s, the interest in neural networks decreased in favor of support vector machines. Finally, another huge step in neural networks was made in 2006 when fast learning algorithm for multi-layer networks started the deep learning field. Now that we have the proper background, we can step further and dive into handwritten digit recognition project. We can split this project in two sub-problems. Okay. First, we would like a way of breaking an image containing many digits onto a sequence of separate images, each containing a single digit. Well, we'll focus on writing a program to solve the second problem. This is classifying individual digits. Because we target a live system, we take live images from a camera. These images are driven through a pre-trained neural network which is implemented in FPGA. One of the biggest challenges in artificial neural network training is the training data set. Normally, one has to use thousands of images for the learning phase, and the final accuracy is tightly related to a good training set. For this reason, we used MNIST dataset, which provides 60,000 images. From the architectural point of view, we have an input layer, 2 hidden layers, and an output layer which contains 10 neurons. Here we have a general overview of the neural network that is used in this project. The most important aspects that we have to keep in mind about this structure are the following. The first one, this is a feed-forward neural network. There are no loops in this network. The information is always fed forward. And the second one, we use 2 hidden layers in our topology, and this meets deep neural network definition loosely. People now routinely train networks with 5 to 22 hidden layers. But why did we choose this topology? Well, there can be quite an art to the design of hidden layers. In particular, it's not possible to sum up the design process of the hidden layers in a few rules of thumb. Instead, we use heuristics for the hidden layers, which help people to get the behavior they want out of their nets. We tried out more topologies, and for this one we obtained the best result. The input layer of the network contains neurons encoding the values of the input pixels. Our data training set for the network consists of many 28 by 28 pixel images of scanned handwritten digits. So the input layer contains 784 neurons. The input pixels are grayscaled, with a value of 0.0 representing white, a value of 1.0 representing black, and in-between values representing gradually darkening shades of gray. The second layer of the network is a hidden layer. This one contains 16 neurons, and each neuron from this hidden layer is connected with each neuron from the previous input layer. After that, we have another hidden layer, identical with the first one. Using this topology of 2 hidden layers, we can identify more abstract and more detailed features from the input images. The output layer of the network contains 10 neurons. These ones are numbered from 0 to 9. After processing the pixels from the input layer, each neuron of the output layer contains a value different from 0. This value does not represent the probability. Instead, it quantifies the confidence of each neuron in the digit that it represents. We pick the neuron with the highest value, and its index represents the identified digit. If we dive deeper in our neural network, we reach the fundamental cell of our system, the artificial neuron. There are many artificial neuron models developed by researchers over the years. Each model represents a mathematical function that describes the functionality observed in biological neurons. What we have used is widely known as sigmoid neuron. The most important feature of this model can be observed from the shape of its activation function. Small changes in its weights and biases will cause only a small change in its output. That's the crucial fact that will allow a network formed from sigmoid neurons to learn. Now that we have a design of our neural network, how can it learn to recognize digits? The first thing we'll need is a data set to learn from, or a so-called training data set. We use the MDIS data set, which contains many images of scanned handwritten digits, together with their correct classification. The learning process of a neural network is accomplished by fine-tuning the weights and biases of each neuron. For this purpose, we use a quadratic cost function, also known as mean squared error, which quantifies the difference between the expected value and the actual neural network output for a given training set. And the main objective of the learning phase is to reduce the cost function, right? The basic algorithm for this purpose is called gradient descent. So we train our neural network using MDIS dataset, gradient descent, and Python scripting on a workstation. Next, we'll test our network. For this, we'll ask it to recognize images which aren't in the training set. This whole process is known as supervised learning. This is the board that we used in our project. It is a board that we design and sell. We chose this specific board because it had big enough FPGA that we thought we are going to fit in, and it had a needed imaging interfaces like Raspberry Pi connector for PCAM, 5C camera, HDMI input and output interfaces, and some GPIO connectors to display the final result. The core of this board is a Zinc 7020 SoC chip, which encapsulates an ARM processor, dual-core A9, and 85,000 logic cells FPGA. Also, this board is equipped with 1 gigabyte of DDR3L memory, perfect for video processing applications. The main input interface for our system is the PCAM 5C. It is a 5 megapixel color camera capable of 1080 pixels at 30 Hertz frequency. It provides high-speed interface compatible with CSI2 and Xilinx MIPI core. Digilent offers a free IP that can be used to interact with this module. Here we have an overview image of the final project. We can interact with the system by writing down a digit on a piece of paper, which will be placed in the camera's field of view. From this point, we have to pass the input image through a set of transformation in order to obtain an image with the same format as the images used in the training phase. These operations are spread between FPGA and ARM processor, taking into account which transformation is suitable for FPGA parallelization and which are not. So in FPGA, we take care of the following. We capture the image, we scale it, after that we convert the image to grayscale, and in the end we apply a threshold to perform a black and white binarization. And for teaching purposes, the threshold can be modified live using a B-mode encoder. The MDIS dataset has digits centered and scaled. However, when interacting live with the system, we do not constrain the user to write a perfect centered digit. As you can see in the images, the digits are far apart from the center and are not scaled properly. This can lead to wrong results because the neural network was not trained with such examples. For this reason, we perform a correction in 2 phases. The first one is bounding box search, in which we look for a rectangle with the minimum area which contains the digit. The second one is the center and scale phase, which rebuilds the image around the found rectangle and scales it to the right dimensions. These 2 phases are implemented in ARM processor. Okay, so until now we discussed some general notions about neural networks, and I gave you some details about how did we approach the project. In this point, I would like to show you an implementation detail which is specific to the adopted architecture. We talk a little about artificial neurons, and maybe you have the intuition on how they are implemented and how they interact with the whole network on a regular processor. Even that, we run a hybrid system. We use a programmable logic, an FPGA, to implement the neurons, and these aspects change the things a little. As you can see, there are some multiplication and addition operation. These ones are performed using the DSPs inside FPGA. The parameters that are obtained after the training
developing game-changing embedded intelligence mit Chip-Token von Networks. Der Zutritt ist für alle Messebesucher und Kongressteilnehmer kostenfrei. The keynote Developing Game-Changing Embedded Intelligence with Chip-Token from Networks will start at 1:30 p.m. in the Nürnberg Convention Center House, Room Sydney. The access is free of charge for all visitors and Congress participants.
Okay, so the parameters that were obtained in the training phase, the biases and the weights for each neuron, is stored in FPGA block-RAM. And finally, the sigma activation function is obtained using the FPGA lookup table. We use fixed point Q4.11 representation because this one is more suitable for FPGA processing than the floating point representations. We evaluated the system, and the recognition rate of the training network or on MNIST data set is 95.2%. On the other hand, live recognition rate is highly dependent on digit skew. The system performance was tested in two different configurations for two different tasks. In all cases, we obtain a better result by offloading the ARM processor and accelerating some functions in FPGA. Okay, so we are waiting you in our booth to try the demo. You can see our other products there as well. If you have any questions about this project, let me know now, or you can walk up to our booth and see you there. Thank you for attending.